Hello there, and welcome back to the Science Sleepy Minds. Tonight you are standing at the very edge of everything you have ever known. Picture it. You are hovering somewhere past Neptune, past the last signpost of the familiar solar system, and all around you is a darkness so complete it almost feels like velvet pressed against your skin. The sun, from out here, is barely a bright star. You can cover it with the tip of your pinky finger. And somewhere in this freezing, silent expanse, something enormous might be moving. Something no human eye has ever seen. Something 5 to 10 times the mass of Earth, drifting along an orbit so vast it takes thousands of years to complete a single lazy lap. You probably will not survive this journey, by the way, not because of danger, but because the sheer scale of what we're about to explore tonight tends to put even the most stubborn insomniac to sleep before we reach the halfway point. That is sort of the idea. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And hey, while you're settling in, drop a comment and let me know where you're listening from tonight. Tell me your city, your country, your local time. I always love reading those. There is something wonderful about knowing that someone in Tokyo at 3 a.m. and someone in Sao Paulo at midnight are both drifting off to the same story about a ghost planet. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You take a breath. The cold out here would freeze that breath solid in a fraction of a second. But this is your imagination, and your imagination has excellent central heating, so you float, you look around, and you wonder. Is there really something out there? A massive, undiscovered world hiding in the blackness at the fringes of our solar system? That is the question astronomers have been arguing about, with increasing intensity, for the better part of a decade now. And tonight, we're going to trace every twist of that argument, from the first suspicious clues to the latest telescope surveys, from bold predictions to stubborn skepticism, all the way to the threshold of an answer that might finally be within reach. But before we chase a planet that may or may not exist in the outermost dark, you need to understand something fundamental about how humans have found new worlds in the past. Because here is the thing that makes this story so tantalizing. We have done this before. We have looked at the motion of known planets, noticed something odd, done some math on the back of what might as well have been a napkin, and pointed a telescope at a patch of sky where nothing was supposed to be, only to find a brand new world staring back at us. It has happened. It is not fantasy. It is historical fact. And that precedent is exactly what keeps the hunt for Planet 9 alive, even when the doubters raise very reasonable objections. The story of finding planets by their gravitational fingerprints really begins with Uranus, which, yes, is impossible to say in a sleepy video without at least one person in the comments making the joke, and that is fine. You go ahead and get it out of your system. Uranus was discovered in 1781 by William Herschel, a German-born musician living in England who had taken up astronomy as what you might generously call an aggressive hobby. Herschel was not looking for a planet. He was conducting a painstaking survey of the night sky with a homemade telescope, cataloguing stars when he noticed something that did not look quite right. A small, faintly greenish disk that moved against the background stars from night to night. At first, he thought it was a comet. Astronomers back then tended to think most new moving objects were comets because, frankly, new planets were not supposed to exist. The solar system had 6 planets. Everyone knew that. It was settled science. Except it was not settled at all, because Herschel had just accidentally doubled the known size of the solar system. Now, what happened next is where the story gets interesting for our purposes tonight. Once astronomers calculated the orbit of Uranus using Newton's shiny new laws of gravity, they found that the planet did not behave. It did not follow its predicted path. It moved a little too fast here, a little too slow there, as though something unseen was pulling on it. Some people suggested that maybe Newton's laws were slightly wrong at great distances. Scholars still argue whether that early skepticism about Newtonian gravity delayed the search for an eighth planet or actually spurred it on. But a handful of mathematicians decided to take the optimistic approach. They assumed the laws were fine and that the wobble was caused by the gravitational influence of an undiscovered planet even farther from the Sun. Two of them, the Frenchman Urbain Le Verrier and the Englishman John Couch Adams, independently worked out where this hypothetical planet should be. Le Verrier sent his prediction to the Berlin Observatory in September of 1846. The astronomer Johann Galle pointed his telescope at the coordinates that very night, and there it was, a pale blue dot, almost exactly where Le Verrier said it would be, Neptune, a world found not by looking but by thinking, by mathematics and gravitational logic. It remains one of the most elegant discoveries in the history of science, and it established a template that echoes directly into tonight's story. If the known objects in your solar system are not moving the way they should, maybe something you have not found yet is doing the pulling. That template, that seductive idea that gravity can betray the presence of hidden worlds, is the very engine driving the search for Planet 9. And it is why, whenever someone discovers that a cluster of distant icy bodies are orbiting in a pattern that seems too organized to be coincidental, a certain kind of astronomer gets a very specific gleam in their eye. You know the gleam. It is the gleam of someone who thinks they're about to find a planet. You, meanwhile, are floating in the dark, watching the faintest glimmer of the sun, and you feel the first gentle tug of sleep at the edges of your thoughts. But not yet. We have a long way to travel before morning, and the next stretch of this journey takes us to a little frozen world that broke 1 billion hearts. You drift inward just a little, back toward the sun, though inward is a generous word when you're still billions of kilometers from anything resembling warmth. The year is 1781 again in your mind, and Herschel's accidental discovery of Uranus has just rearranged humanity's understanding of the solar system. But the real magic trick, the one that matters most for our story tonight, came 65 years later with Neptune. And you need to sit with that triumph for a moment longer, because the method behind it, the idea that you can deduce the existence of an unseen world purely from its gravitational tug on the world you can see, is not just historically interesting. It is the philosophical backbone of everything the Planet 9 hunters are doing right now, tonight, as you listen to this. Think about what Le Verrier and Adams actually accomplished. They did not have computers. They did not have calculators in any modern sense. They had quill pens, reams of paper, and Newton's equations, and they used those tools to predict the location of a world no human had ever glimpsed. Le Verrier reportedly performed calculations so laborious that it took him months of daily grinding mathematical work. There is a quirky footnote to this story that does not get enough attention. Le Verrier was, by most accounts, extraordinarily difficult to work with. His colleagues at the Paris Observatory found him so abrasive that many of them resigned rather than continue under his direction. So the man who found Neptune by pure intellect was also the man most likely to clear a room at a dinner party. Genius and charm, it turns out, are not always packaged together. But here is where the discovery of Neptune sets a trap. A beautiful, seductive trap that astronomers have been falling into ever since. The success was so stunning, so clean, that it created an expectation. If the orbits of known objects look strange, there must be another planet causing the strangeness. And that expectation led directly to one of the most famous wild goose chases in astronomical history. You see, after Neptune was found, astronomers kept watching Uranus and Neptune, and they thought they detected still more wobbles, more tiny discrepancies in the orbits. The obvious conclusion, following the Neptune playbook, was that yet another planet must exist even farther out. A planet X. The search for this hypothetical world consumed decades of telescope time and professional ambition, and it is the direct ancestor of tonight's Planet 9 saga. The most famous hunter in this chapter was Percival Lowell, an American astronomer with family money, a flair for drama, and an observatory in Flagstaff, Arizona, that he built largely to pursue his personal obsessions. Lowell is perhaps best remembered for his fervent belief that Mars was crisscrossed by artificial canals built by an intelligent civilization, a claim that was romantic, wildly popular with the public, and completely wrong. But Lowell also spent the last years of his life searching for Planet X. He made predictions about where it should be based on those supposed orbital residuals of Uranus and Neptune. He searched and searched. He did not find it. He died in 1916, frustrated and unfulfilled, which is a melancholy note but also a reminder that the universe does not owe you a discovery just because you really, really want one. 14 years after Lowell's death, however, a young astronomer named Clyde Tombaugh, working at Lowell's own observatory, did find something. Tombaugh was 24 years old, had no college degree at the time, and had been hired essentially as a junior technician to continue the Planet X search. His method was beautifully tedious. He used a device called a blink comparator, which allowed him to rapidly switch between two photographic plates of the same star field taken on different nights. If anything had moved between the two exposures, it would appear to jump back and forth. On February 18th, 1930, Tombaugh noticed a tiny dot doing exactly that. It was moving against the background stars. It was real. The world would call it Pluto. Now, the celebration was enormous. The discovery made international headlines. Lowell Observatory had vindicated its founder's quest. A schoolgirl in Oxford, 11-year-old Venetia Burney, suggested the name Pluto over breakfast, and it stuck. There is your quirky tidbit for this stretch of the night. An 11-year-old named a planet while eating toast, and that name has outlived almost everything else about the discovery's original context. But there was a problem, and it was a problem that would take decades to fully appreciate. Pluto was tiny, embarrassingly tiny. When it was first discovered, astronomers assumed it was roughly Earth-sized because that was what the Planet X predictions required. But as observations improved over the following decades, Pluto kept shrinking. By the 1970s, estimates had dropped dramatically, and when Pluto's moon Charon was discovered in 1978, astronomers could finally calculate Pluto's mass accurately using orbital mechanics. The result was devastating for anyone who wanted Pluto to be Planet X. It was far too small. Its mass was roughly 1/6 that of Earth's moon. There was simply no way this little ice ball was causing the orbital perturbations that Lowell and others had predicted. Scientists still debate whether Tombaugh's discovery was a genuine case of serendipity, a happy accident where he found a real object that had absolutely nothing to do with the mathematical predictions that motivated the search, or whether there was some subtle observational bias guiding him toward that particular patch of sky. And this is where the story gets its bittersweet twist. Pluto, the world discovered in the search for a massive hidden planet, turned out to be neither massive nor hidden in the way anyone expected. It was something else entirely, a representative of a whole population of icy bodies that astronomers would not begin to discover for another 6 decades. Pluto, in a sense, was the first clue that the outer solar system was far more crowded and far more strange than anyone had imagined. And that strangeness, that crowded, icy wilderness beyond Neptune, is exactly where the modern case for Planet 9 begins to build. You feel yourself drifting now, pulled not by gravity but by curiosity, deeper into the dark, past Pluto's faint glimmer, into a region of the solar system where sunlight is just a rumour and the cold is absolute. You linger near Pluto for a while, watching it turn slowly in the dim light. It is smaller than you expected, smaller than Earth's moon, smaller even than some of the moons of Jupiter and Saturn. Its surface is a patchwork of nitrogen ice and frozen methane, with a heart-shaped glacier that became oddly famous when the New Horizons spacecraft flew past in 2015 and beamed back those stunning photographs. You remember those images, maybe? The internet fell in love with Pluto all over again, which was ironic given what had happened to it 9 years earlier, the demotion. You have to talk about the demotion. In August 2006, the International Astronomical Union held its General Assembly in Prague, and the roughly 400 astronomers who stayed until the final vote did something that made children cry and adults write angry letters. They redefined the word planet in a way that excluded Pluto. The new definition required that a planet must orbit the Sun, must have enough mass for gravity to pull it into a roughly spherical shape, and crucially, must have cleared the neighbourhood around its orbit. Pluto satisfied the first two conditions just fine, but that third one was the killer. Pluto's orbit is cluttered with other icy objects. It shares its orbital space with thousands of them. It has not cleared its neighbourhood, and so, by the new rules, Pluto was reclassified as a dwarf planet. The outcry was immediate and in some corners genuinely furious. There were bumper stickers, there were protest songs. The state legislature of New Mexico, where Clyde Tombaugh had lived, passed a resolution declaring that Pluto would always be considered a planet within state borders, which is a charming but legally meaningless gesture, and also one of the most endearing acts of planetary loyalty you will ever encounter. But behind the emotional drama, the real scientific story was far more interesting than a bureaucratic name change. The reason Pluto got demoted was not spite, it was context. By 2006, astronomers had begun discovering other objects in the outer solar system that were comparable in size to Pluto, and one of them, a world called Eris, was initially measured as being slightly more massive. If Pluto was a planet, then Eris probably had to be one too. And if Eris was a planet, then what about the dozens of other large icy bodies being discovered in that same general region? Were they all planets? Were we going to end up with 50 planets? 100? The IAU decided to draw a line, and Pluto ended up on the wrong side of it. The man most directly responsible for Pluto's downfall, at least in the popular imagination, was Mike Brown, a planetary astronomer at Caltech. Brown discovered Eris in 2005, and that discovery was the catalyst for the reclassification debate. He leaned into the role with a certain cheerful defiance, even titling his memoir How I Killed Pluto and Why It Had It Coming. He seemed to enjoy the controversy, or at least to understand that scientific progress sometimes requires uncomfortable demolition work. Scientists still argue whether the IAU's definition of planet is scientifically rigorous or merely a pragmatic compromise that will eventually be revised. Some planetary scientists, including members of the New Horizons team, have never accepted the demotion and continue to refer to Pluto as a planet in their published work. It is one of those debates that reveals how much of science is not just about data, but about definitions, about the words we choose and the categories we build. Now here is the twist that makes this relevant to tonight. Mike Brown, the man who killed Pluto, would go on to become one of the two primary architects of the Planet 9 hypothesis. The same astronomer who took a planet away would, a decade later, try to give us a new one. The universe has a sense of humour, and it is exactly the kind of dry, ironic humour that you would expect from a cosmos that hides its biggest objects in the darkest corners. But before Brown and his colleague Konstantin Batygin entered the picture, there was a growing pile of strange observations that needed explaining. And most of them came from Pluto's neighbourhood, or rather, from the vast icy region that Pluto had turned out to be just one small citizen of. You see, Pluto's weird orbit had been bothering astronomers for decades before the demotion controversy. Unlike the 8 major planets, which orbit the Sun in roughly the same flat plane and in nearly circular paths, Pluto's orbit is tilted. It is angled about 17 degrees relative to the plane of the solar system, and it is highly elliptical, so much so that for part of its 248-year journey around the Sun, Pluto actually dips inside Neptune's orbit. For 20 years out of every 248, Pluto is technically closer to the Sun than Neptune is. This happened most recently between 1979 and 1999, which means that for a good chunk of your parents' or grandparents' lives, the so-called 9th planet was not even the outermost one. That odd orbit was one of the first hints that the outer solar system does not play by the same tidy rules as the inner planets. And as astronomers discovered more and more objects beyond Neptune throughout the 1990s and 2000s, the hints multiplied. Some of these objects had orbits that were even more extreme than Pluto's. Some were tilted at wild angles. Some travelled on paths so elongated that they spent most of their lives in the frigid dark, thousands of astronomical units from the Sun, before swooping briefly inward on orbits that took thousands of years to complete. One by one, these discoveries painted a picture of an outer solar system that was far more dynamic, far more sculpted, and far more mysterious than the neat clockwork model you probably learned about in school. Something had shaped these orbits. Something had pushed and pulled these icy worlds into their current configurations. And the biggest question, the one that would eventually ignite the Planet 9 debate, was whether that something was still out there, still orbiting, still invisible, still waiting. You pull your blanket a little tighter. The cold out here is not physical, but it is real in a different way. It is the cold of the unknown, and it is pulling you deeper. You float past Pluto now, leaving its heart-shaped glacier behind like a farewell card pinned to the edge of familiarity. Ahead of you is the Kuiper belt, and you need to understand this place because it is where the entire Planet 9 mystery lives and breathes. The Kuiper belt is not a belt in any visual sense. You will not see a ring of rocks like the asteroid belt between Mars and Jupiter, which itself is far more sparse than movies have led you to believe. The Kuiper belt is more like an enormous diffuse donut of icy debris stretching from roughly Neptune's orbit at 30 astronomical units from the Sun, out to about 50 astronomical units, and then trailing off into an even more tenuous region beyond. 1 astronomical unit is the distance from the Earth to the Sun, about 150 million kilometres, so when we say 50 astronomical units, we're talking about a distance so vast that light itself takes nearly 7 hours to cross it. You could fit a lot of loneliness in that much space. The Kuiper belt was theorised long before it was observed. In 1951, the Dutch-American astronomer Gerard Kuiper suggested that a belt of icy bodies might exist beyond Neptune, remnants of the original solar nebula that never coalesced into a full-size planet, because the material out there was too spread out and the gravitational influences too weak. It was a reasonable prediction, but it took 4 decades before technology caught up. The first confirmed Kuiper belt object other than Pluto, a dim little world designated 1992 QB1, was discovered in 1992 by David Jewett and Jane Liu using the University of Hawaii's telescope on Mauna Kea. That discovery cracked open a door, and behind it was a flood. By the early 2000s, hundreds of Kuiper belt objects had been catalogued. By the 2000s, the count was in the thousands, and buried in that growing catalogue were some very peculiar orbits. Here is where you need to pay attention, or at least as much attention as your increasingly drowsy brain will allow. Among the thousands of known Kuiper belt objects, there is a small but significant subset that behaves strangely. These are the extreme trans-Neptunian objects, sometimes called ETNOs, and their orbits share a set of features that, statistically, should not all line up the way they do. Their orbits are highly elongated, stretching far beyond the main Kuiper belt. They have similar orientations in space, meaning their orbital ellipses point in roughly the same direction. And many of them are tilted at similar angles relative to the flat plane of the solar system. Imagine you're standing in a field and you notice that a dozen different wind vanes, scattered across the landscape, are all pointing the same way. You would reasonably conclude that something, a prevailing wind, is pushing them into alignment. The extreme trans-Neptunian objects are the wind vanes. The question is, what is providing the wind? The first person to really bang the drum about this clustering was Chad Trujillo, who, along with Scott Shepherd, discovered a distant object called 2012 VP113 in 2014. This object, affectionately nicknamed Biden because of its VP designation, had an orbit that was remarkably similar in orientation to Sedna, another extreme trans-Neptunian object discovered back in 2003. Sedna itself had been a puzzle for years. Its orbit is so elongated that it takes over 11,000 years to go around the Sun, and at its most distant point, it is nearly 1,000 astronomical units away. Nothing in the known solar system could explain how Sedna got onto such an orbit. It was too far from Neptune to have been scattered by that planet's gravity. It was too close to have been influenced by passing stars. Sedna was, in the words of its discoverer Mike Brown, the most unusual object in the solar system. And when 2012 VP113 showed up with a suspiciously similar orbit, Trujillo and Shepherd suggested in their paper that a large unseen planet might be responsible for shepherding these objects into their aligned paths. Now, a sample size of 2 is not exactly overwhelming evidence. Scientists still argue whether 2 aligned orbits constitute a genuine pattern or merely a coincidence amplified by human pattern recognition, which is after all the same cognitive engine that finds faces in clouds and conspiracies and coincidences. But the clustering did not stop at 2. As more extreme trans-Neptunian objects were discovered over the following years, the alignment persisted. Objects like 2013 RF98, 2004 VN112, and 2010 GB174 all showed orbital characteristics that seemed to cluster in a way that random chance would not easily produce. The statistical significance of this clustering became the central battleground of the Planet 9 debate, and it remains contested to this day. There's a quirky detail worth mentioning here. The study of these distant icy orbits relies heavily on a quantity called the argument of perihelion, which sounds like the name of a philosophy dissertation, but is actually just a technical term describing the orientation of an object's closest approach to the Sun within its orbital plane. Trujillo and Shepherd noticed that the arguments of perihelion for several extreme trans-Neptunian objects were clustered near 0 degrees, which would be unlikely if their orbits were randomly distributed. It was a subtle clue, the kind of thing you could easily dismiss if you were not paying close attention, but it was enough to set a small corner of the astronomical community buzzing. And buzzing is exactly what was happening at Caltech, where Mike Brown and a young theoretical astrophysicist named Konstantin Batygin were about to take this buzzing and turn it into a full-blown scientific earthquake. But that earthquake, and the paper that triggered it, is waiting for you just ahead in the dark. You can almost feel the rumble of it beneath your feet, even though there is no ground out here, just cold and silence, and the faintest hint of something enormous turning slowly in the void. The rumble arrives in January 2016, and it arrives with a kind of quiet confidence that only comes from people who have checked their math 3 times and still cannot believe what it is telling them. Konstantin Batygin and Mike Brown published their paper in the Astronomical Journal, and the title is deliberately understated as scientific titles tend to be. Evidence for a distant giant planet in the solar system. No exclamation marks, no dramatic flourishes, just a calm declaration that the data, the simulations, and the gravitational logic all point toward the same conclusion. Something big is out there. You need to meet these two properly, because their partnership is one of those odd couple collaborations that science occasionally produces and that Hollywood would reject as too on the nose. Mike Brown, as you already know, is the Pluto killer. A seasoned observational astronomer with decades of experience hunting for objects in the outer solar system. He is practical, data-driven, and has the weathered skepticism of someone who has spent too many cold nights at telescopes watching for things that usually turn out to be nothing. Konstantin Batygin, on the other hand, was in his late 20s when the Planet 9 paper was published. He is a theoretical astrophysicist, a musician who plays in a rock band, and by most accounts he approaches orbital mechanics with the enthusiasm of someone who genuinely finds differential equations beautiful. Brown looks at the sky. Batygin looks at the equations. Together they made a case that shook the planetary science community awake. Their argument went like this. They started with 6 extreme trans-Neptunian objects, whose orbits were well enough determined to be reliable. These 6 objects all had orbits that were elongated in roughly the same direction and tilted in a similar way. The probability of this alignment happening by pure chance, Brown and Batygin calculated, was about 0.007%. That is roughly 1 in 15,000. Not impossible, but deeply unlikely, the kind of odds that make a scientist sit up very straight in their chair and start looking for a cause. The cause they proposed was a planet, not a small one, not another Pluto-sized ice ball, a genuine giant, somewhere between 5 and 10 times the mass of Earth, orbiting the Sun on a hugely elongated path with a semi-major axis of roughly 400 to 800 astronomical units. To put that in perspective, Neptune orbits at about 30 astronomical units. This hypothetical planet would be 10 to 20 times farther away than Neptune at its average distance, and at the far end of its orbit, it could be over 1,000 astronomical units from the Sun. Its orbital period, the time it takes to complete one trip around the Sun, would be somewhere between 10,000 and 20,000 years. The last time this planet was at its closest approach to the Sun, if it exists, humans were painting animals on cave walls and figuring out agriculture. That is the scale of time we're dealing with here. But the paper did not just point to the clustering and shrug. Batygin ran extensive gravitational simulations, modelling what would happen if you placed a planet with the proposed characteristics into the outer solar system and let it interact with the known extreme trans-Neptunian objects over billions of years. The results were striking. The simulated planet naturally produced the kind of orbital clustering observed in the real data. It herded the distant objects into aligned orbits through a mechanism called secular gravitational interaction, which is essentially a slow, continuous exchange of angular momentum between the planet and the smaller bodies over millions of orbital cycles. Think of it like a parent on a playground who is not pushing any individual swing directly, but whose mere presence and gravitational influence causes all the swings to gradually synchronize. It is a gentle process, but over billions of years, gentle processes can sculpt entire populations of orbits. And then the paper did something unexpected. It made a prediction that had nothing to do with the original clustering. The simulation showed that a Planet 9 with the proposed orbit would also produce a population of objects with orbits perpendicular to the plane of the solar system. High inclination objects, tilted at extreme angles, essentially orbiting the Sun in a direction that is almost at right angles to everything else. And here is the beautiful part. Such objects already existed in the observational record. A handful of extreme trans-Neptunian objects with bizarrely tilted orbits had already been discovered, and nobody had a good explanation for them. Planet 9, according to Batygin and Brown's model, explained them naturally. This was not retrofitting. This was a prediction confirmed by pre-existing data, which is exactly the kind of evidence that makes physicists start nodding slowly and reaching for their coffee. The reaction from the scientific community was a mixture of excitement, caution, and healthy skepticism. Some astronomers called it the most compelling evidence for a new planet since the discovery of Neptune. Others pointed out that 6 objects is a very small sample, that observational biases could be skewing the data, and that extraordinary claims require extraordinary evidence. Scientists still argue whether the statistical significance of the clustering is robust enough to support such a dramatic hypothesis, or whether it is an artifact of the limited and biased surveys that discovered these objects in the first place. The debate even now has not been fully resolved. Brown and Batygin, for their part, seem to welcome the skepticism. Brown said publicly that he would give the hypothesis about a 70% chance of being correct, which is an unusually honest and specific admission of uncertainty from a scientist announcing a major claim. He also said something that stuck with a lot of people. He said that the best way to prove or disprove the hypothesis was simply to find the planet. Point a telescope at the right patch of sky, and either it is there or it is not. The math could argue back and forth forever, but a photograph would settle it. You like the simplicity of that. Find it, or do not. The universe, for all its complexity, sometimes offers beautifully binary questions. But finding it, as you are about to discover, is a problem of almost absurd difficulty. And the darkness around you, vast and indifferent, is not giving up its secrets easily. You try to picture it now, the planet itself, not the math, not the orbital diagrams, not the arguments for and against, but the actual world. If Planet 9 exists, what would you see if you could somehow teleport to its location and hover beside it? The answer, frustratingly, is that you would probably see almost nothing, and that is a big part of the problem. Based on Batygin and Brown's models and subsequent refinements by other research groups, Planet 9 is most likely what astronomers call a super-Earth, or a mini-Neptune. Those terms describe a category of planet that is extremely common in our galaxy, but entirely absent from the inner solar system. A super-Earth is a rocky or icy world with a mass between about 2 and 10 times that of Earth. A mini-Neptune is similar in mass but wrapped in a thick envelope of hydrogen and helium gas, like a smaller, colder version of Neptune itself. Planet 9, if it exists, probably falls somewhere in that range, perhaps around 6 Earth masses, with a radius roughly 2 to 4 times that of Earth. It would be a substantial world, bigger than Earth, smaller than Neptune, and utterly invisible to the naked eye from any vantage point on our home planet. The reason for that invisibility is distance. Remember, this object is predicted to orbit at an average distance of perhaps 500 to 600 astronomical units from the Sun, with its farthest point potentially exceeding 1,000 astronomical units. At those distances, sunlight is inconceivably faint. The intensity of light drops off with the square of the distance, so an object 500 astronomical units from the Sun receives only 1/250,000th sunlight that Earth does, and the light that does reach Planet 9 has to bounce off its surface and travel all the way back, covering that enormous distance a second time before it reaches a telescope on Earth. The round trip means the apparent brightness drops with the 4th power of the distance. You do not need to remember the math. You just need to understand that the result is a world so dim that it makes Pluto look like a spotlight. Current estimates suggest that Planet 9, at its predicted distance, would have an apparent magnitude somewhere around 25 or fainter. For reference, the faintest stars you can see with your unaided eye on a perfectly dark night are about magnitude 6. Every 5 magnitudes represent a factor of 100 in brightness. So magnitude 25 is roughly 10 billion times fainter than the faintest star you can see without a telescope. 10 billion. You could stare at the exact right patch of sky for your entire life, and you would never, ever see it. You would need one of the largest telescopes on Earth, ideal atmospheric conditions, and a very long exposure time, and even then, you would be hunting for a faint smudge among millions of other faint smudges. There's a quirky detail about Planet 9's predicted temperature that captures just how alien this world would be. At 500 astronomical units from the Sun, the equilibrium temperature, the temperature an object reaches just from absorbing and re-emitting sunlight, is roughly minus 220 degrees Celsius. But Planet 9 might actually be slightly warmer than that, if it has retained some internal heat from its formation. As planets tend to do, it could be radiating a faint glow of infrared energy. This residual warmth is what makes some astronomers hopeful that infrared surveys might eventually detect it, but we will get to that strategy later. For now, just picture a world barely warmer than the cosmic background, glowing faintly in wavelengths your eyes cannot see, drifting through a darkness that stretches in every direction for billions of kilometers. Its orbital period is another source of quiet awe. At somewhere between 10,000 and 20,000 years, a single orbit of Planet 9 around the Sun spans the entirety of recorded human civilization. If Planet 9 was at perihelion, its closest point to the Sun, when the first cities were being built in Mesopotamia, it would only now be approaching the far end of its orbit, the aphelion, the most distant and coldest point in its journey. It moves with a patience that makes glaciers look impulsive, and because its orbit is so elongated, its speed varies enormously. Near perihelion, it would be moving relatively quickly, perhaps fast enough that its motion against the background stars would be detectable over a period of months. Near aphelion, it would be crawling, barely shifting position from year to year, a nearly motionless pinprick of cold light. Scientists still argue about the orbital inclination of Planet 9, meaning how tilted its orbit is relative to the plane of the solar system. Early estimates suggested an inclination of about 15 to 25 degrees, which would place it well above or below the band of sky where most planet searches have traditionally focused. This is significant because many of the deepest sky surveys have concentrated on the ecliptic, the plane in which the known planets orbit. If Planet 9's orbit is substantially tilted, it could be hiding in a region of sky that has simply not been surveyed to sufficient depth. It is like losing your keys in the living room but spending all your time searching the kitchen because the light is better there. The shape of the orbit also matters for detection. If Planet 9 is currently near aphelion, it would be at its faintest and its slowest, making it incredibly difficult to spot. If it is closer to perihelion, it would be brighter and moving faster, but it would also be in a more crowded region of sky where distinguishing it from background objects becomes its own challenge. Batygin and Brown's original paper left a wide range of possible current positions, spanning a significant arc of sky. Subsequent work has narrowed this range somewhat, but the search area remains daunting. You squint into the darkness, trying to see what the telescopes cannot yet see. Somewhere out here maybe, a cold world is turning. Or maybe it is not. Maybe the darkness is just darkness. But the thought of it, the sheer stubborn possibility keeps you looking. And so the search begins, and you quickly discover that looking for Planet 9 is less like finding a needle in a haystack and more like finding a specific grain of dark sand on a beach at midnight while wearing sunglasses. The theoretical prediction is one thing. The observational reality is something else entirely. Batygin and Brown told the world roughly where to look, roughly how bright the object should be, and roughly how fast it should be moving. Armed with those parameters, you might think it would be a straightforward matter of pointing the right telescope at the right patch of sky and waiting. You would be wrong, and the reasons you would be wrong are instructive in a way that reveals just how hard astronomy actually is when you move beyond the pretty pictures and inspirational sound bites. The first problem is the sheer size of the search area. Even after Batygin and Brown narrowed the predicted orbital parameters, the region of sky where Planet 9 could plausibly be located spans hundreds of square degrees. For context, the full moon covers about half a degree of sky. So we're talking about a search area equivalent to hundreds of full moons, and within that area, every single point of light needs to be examined, compared against known catalogues, and checked for motion. The most powerful survey telescopes can image large swathes of sky in a single night, but they generate terabytes of data that must be processed, filtered, and analysed. The computational challenge is almost as daunting as the observational one. The second problem is depth. Planet 9, as we discussed, is extraordinarily faint. To detect an object at magnitude 25 or beyond, you need long exposure times on large telescopes, but large telescopes are in high demand. Observing time on instruments like the Subaru telescope on Mauna Kea, which Brown and Batygin have used extensively in their search, is allocated through competitive proposal processes. You do not just show up and say you would like to spend the next 6 months looking for a planet that might not exist. You submit a proposal, it gets reviewed by a committee, and you receive a limited number of nights. Those nights might have bad weather. The seeing conditions might be poor. The moon might be too bright. Any number of factors can ruin a night of observing, and each lost night is time you cannot get back. The third problem is confusion with background objects. The region of sky where Planet 9 is most likely to be found, based on current predictions, includes parts of the Milky Way's galactic plane. This is the densest, most crowded part of the night sky, packed with billions of stars whose combined glow creates a luminous band. Trying to identify a faint, slow-moving object against this backdrop is extraordinarily difficult. A quirky detail about this particular challenge is that some of the most sophisticated detection algorithms used in the search were originally developed for finding asteroids, which move much faster and are much closer. Adapting those algorithms for an object that barely moves from month to month and is billions of times farther away required significant retooling, and even the best algorithms produce false positives that must be laboriously checked by human eyes. Brown himself has spoken publicly about the emotional toll of the search. He has described nights at the telescope when a promising candidate turns out to be an artifact, a faint galaxy, or a cosmic ray hit on the detector. Each false alarm carries a little sting of disappointment that accumulates over months and years. He has also described the opposite sensation, the electric jolt of seeing something that looks right, that moves at the right speed in the right direction, only to realise after further analysis that it is something mundane. The search for Planet 9 is, in this sense, an exercise in managing hope, which is not a skill they teach you in graduate school but probably should be. There is also the question of whether Planet 9 might have already been photographed without anyone realising it. Archival data from previous sky surveys, going back decades, could contain images of Planet 9 hiding in plain sight among millions of other faint sources. Several teams have conducted searches of archival data from surveys like the Wide Field Infrared Survey Explorer, known as WISE, and the Panoramic Survey Telescope and Rapid Response System, known as PAN-STARRS. These searches have not found Planet 9, but they have placed useful constraints on where it cannot be. If Planet 9 were brighter than a certain threshold in a particular region of sky, WISE would have detected it. The fact that WISE did not see it means Planet 9 must be either fainter than expected, farther away than expected, or located in a region that WISE did not cover deeply enough. Each non-detection tightens the noose, narrowing the search area but also raising the uncomfortable possibility that the object might not be there at all. Scientists still argue about whether the current non-detection is meaningful. Some point out that the search has only covered a fraction of the predicted search area to the necessary depth, so the failure to find Planet 9 so far is not statistically surprising. Others suggest that the continued absence of a detection should be gradually lowering our confidence in the hypothesis. It is a classic problem in the philosophy of science. How long do you search before absence of evidence becomes evidence of absence? There is no clean answer, and reasonable people disagree. You watch the telescopes in your mind, their great mirrors tilting and tracking, gathering ancient photons from the edge of the solar system. Somewhere in those rivers of data, a cold world might be waiting to be noticed. Or it might not. And the not knowing is its own kind of gravity, pulling you forward through the dark, whispering that the next observation, the next survey, the next algorithm might finally tip the balance. But while Brown and Batygin were scanning the skies with the careful optimism of people who believe their math is sound, a different group of astronomers was sharpening a very different set of arguments, and their message, delivered with the polite brutality that only peer-reviewed science can manage, was simple. What if you are wrong? What if the clustering is not real? What if you are seeing a pattern that the universe never actually drew? The most organised and rigorous pushback came from the Outer Solar System Origins Survey, known as OSOS, a large-scale observational program conducted primarily using the Canada-France-Hawaii telescope on Mauna Kea. OSOS was designed from the ground up to address one of the most insidious problems in astronomy, observational bias. And to understand why their critique matters, you need to understand what observational bias actually means in the context of hunting for distant icy objects. Here is the core issue. When astronomers discover extreme trans-Neptunian objects, they do not find them by scanning the entire sky uniformly. They find them by pointing telescopes at specific patches of sky, during specific seasons using specific instruments with specific sensitivities. Each survey has its own unique footprint, its own depth limits, its own blind spots. An object can only be discovered if it happens to be in the region of sky that a particular survey covered, at a time when it was bright enough to detect, moving at a rate that the survey's detection pipeline could recognize. Objects outside those windows are invisible, not because they do not exist, but because nobody was looking in the right place at the right time with the right tools. This means that the sample of known extreme trans-Neptunian objects is not a random, unbiased selection of all such objects that exist. It is a filtered, skewed subset, shaped as much by the geometry and limitations of our surveys as by the actual distribution of objects in space. And here is where the OSOS team drove their knife in. They argued that the apparent clustering of orbits that Batygin and Brown identified could be entirely explained by these observational biases. The objects appear to be aligned not because some invisible planet is herding them, but because we've only been able to find objects that happen to lie in the directions where our telescopes were pointed. Think of it this way. Imagine you're standing in a dark room with a flashlight, and you can only shine the flashlight in one direction. You see 3 cats sitting in a cluster in that direction. You might conclude that all the cats in the room are clustered together. But if you could turn on the overhead lights, you might find that cats are scattered everywhere, and the apparent cluster was just an artifact of where your flashlight happened to be aimed. The OSOS team was essentially arguing that astronomers had been waving a flashlight around the outer solar system and mistaking the beam pattern for a real structure. To support their argument, the OSOS team did something clever. They meticulously characterized the biases of their own survey, mapping exactly which regions of sky they had observed, to what depth, and with what sensitivity to different orbital types. They then asked whether the extreme trans-Neptunian objects discovered by OSOS showed the same clustering signal that Batygin and Brown had reported. The answer, according to the OSOS team, was no. When they accounted for their survey's specific biases, the clustering disappeared. The orbits of the objects they found were consistent with a uniform, random distribution. No shepherd planet required. This was a significant challenge, and it landed with real force in the planetary science community. The OSOS papers, led by astronomers like Corey Shankman, Samantha Lawler, and Michelle Bannister, were detailed, methodical, and difficult to dismiss. They did not claim to have disproven Planet 9. What they claimed was that the evidence in favour of Planet 9 was weaker than it appeared, because the statistical foundation on which it rested was contaminated by biases that had not been adequately accounted for. Batygin and Brown naturally disagreed. They argued that even when observational biases were considered, the clustering remained statistically significant. They pointed to their 2016 prediction about perpendicular orbits, which was confirmed by objects discovered independently, as evidence that their model had genuine predictive power and was not just a post hoc fit to biased data. The debate became technical, granular, and occasionally heated, the kind of scientific argument that plays out over years in the pages of journals and at conference podiums where astronomers interrupt each other's slides with pointed questions. Scientists still argue whether the Ossos critique fatally undermines the Planet 9 hypothesis, or merely forces its proponents to be more careful about their statistical claims. The truth, as is often the case in science, probably lies in an uncomfortable middle ground. The observational biases are real and significant, and any honest assessment of the clustering evidence must account for them. But the biases may not be sufficient to explain all of the observed features, particularly the perpendicular orbits and certain other dynamical details that the Ossos critique did not fully address. There is a quirky footnote to this whole debate that captures its human dimension. Samantha Lawler, one of the Ossos team's most vocal members, has spoken publicly about the social dynamics of challenging a hypothesis championed by high-profile scientists at a prestigious institution like Caltech. She has described the experience as professionally risky, noting that questioning a popular idea can sometimes attract more hostility than the evidence warrants. Science, for all its ideals of objectivity, is conducted by humans with egos, careers, and institutional loyalties. And the Planet 9 debate, whatever its ultimate resolution, has been a vivid illustration of that fact. You listen to the argument echoing through the void, one side saying look at the pattern, the other saying look at the flashlight, and you realise that the answer might depend on which direction you are facing when you open your eyes. You turn slowly in the dark, letting both arguments wash over you, and you realise that the debate is not just about observations, it is also about simulations. Because one of the strongest pillars supporting the Planet 9 hypothesis is not a photograph or a discovery, but a set of numbers generated inside a computer. Numbers that describe how gravity would sculpt the outer solar system over billions of years if a massive unseen planet were lurking at the edge. Gravitational simulations are the bread and butter of modern planetary science. You cannot wait around for 10,000 years to watch an orbit unfold, so you build a virtual solar system inside a machine, populate it with objects whose masses and positions you know, add in whatever hypothetical body you want to test, and let the clock run forward at a speed that would make Einstein uncomfortable. The computer calculates the gravitational pull of every object on every other object at each tiny time step, updating positions and velocities millions of times over to trace out the long, slow dance of orbits across geological timescales. It is painstaking work, not for the humans sitting at the keyboard, but for the processors humming inside the machine, and the results can be strikingly beautiful. Batygin's simulations were central to the 2016 paper and have been refined repeatedly since then. The basic setup works like this. You start with the Sun, the 4 giant planets, and a disk of small icy bodies representing the primordial Kuiper belt. You then add a Planet 9 with a specific mass, orbit and inclination, and let the simulation run for 4.5 billion years, the approximate age of the solar system. What emerges is a detailed prediction of what the outer solar system should look like today if Planet 9 has been gravitationally stirring the pot since the beginning. The results, as you already know, showed that Planet 9 could naturally produce the clustering of extreme, trans-Neptunian object orbits. But the simulations revealed several other features that were equally compelling and arguably harder for the skeptics to explain away. One of those features was the generation of objects on highly inclined orbits, the perpendicular population that Batygin and Brown predicted before it was confirmed observationally. Another was the production of detached objects, worlds like Sedna whose orbits have been lifted away from Neptune's gravitational influence entirely. In a solar system without Planet 9, producing Sedna-like orbits is difficult. You can invoke passing stars or the gravitational influence of the Sun's birth cluster, but those mechanisms tend to produce a broader range of orbital types rather than the specific clustered pattern observed. With Planet 9, detached objects emerge naturally as a byproduct of the long-term gravitational interaction. Perhaps the most provocative result from the simulations, and one that generated significant discussion in the community, was the suggestion that Planet 9 could explain the obliquity of the Sun. The Sun's rotational axis is tilted about 6 degrees relative to the plane of the planetary orbits. This tilt has been a minor puzzle for decades. In a perfectly formed solar system, you would expect the Sun's spin axis and the orbital plane of the planets to be aligned. 6 degrees is not a lot, but it is not zero, and explaining it requires some mechanism that torqued either the Sun or the planets after formation. Batygin and colleagues published a paper arguing that a distant massive planet on an inclined orbit could, over billions of years, exert a slow gravitational torque on the entire inner solar system, gradually tilting the orbital plane of the planets relative to the Sun's spin axis. The magnitude of the predicted tilt matched the observed 6 degrees surprisingly well. Scientists still argue whether the solar obliquity argument is strong evidence for Planet 9 or merely a suggestive coincidence. Alternative explanations for the tilt exist, including interactions with the Sun's birth cluster and asymmetries in the protoplanetary disk. But the fact that a single hypothesis, one unseen planet, could simultaneously explain the orbital clustering, the perpendicular objects, the detached orbits, and the solar obliquity was undeniably elegant. In science, elegance is not proof, but it is a powerful motivator. When one idea cleans up multiple messes at once, it tends to attract attention and adherence. There is a quirky detail about how these simulations work that is worth savouring. Gravitational n-body simulations, as they're called, are exquisitely sensitive to initial conditions. Tiny changes in the starting positions or velocities of objects can lead to dramatically different outcomes over billions of years. This is a manifestation of chaos, not in the colloquial sense of disorder, but in the mathematical sense of sensitive dependence on initial conditions. It means that no single simulation run can definitively predict what the solar system should look like. Instead, researchers run hundreds or thousands of simulations with slightly different starting conditions and look for statistical patterns in the outcomes. Batygin's results are not the product of one lucky simulation, but of an ensemble of runs that consistently produce similar features. This statistical approach is robust, but it also means that the predictions are probabilistic rather than deterministic. Planet 9 does not guarantee the observed clustering. It merely makes it likely, which is a subtly different and less satisfying claim. You drift through this computational universe, watching virtual planets trace their paths across simulated eons, and you find something oddly soothing about it. The idea that the entire history of the outer solar system can be compressed into a few hours of processing time on a modern computer. Billions of years of gravitational whispers reduced to data files and plots. Somewhere in those files, the ghost of Planet 9 either leaves its fingerprints or does not. And the simulations keep running, refining, converging on an answer that the telescopes have not yet delivered. The simulations make a compelling case, but science is a gladiatorial arena dressed up in tweed, and for every elegant hypothesis, there is a line of contenders waiting to take its place. Planet 9 is not the only explanation for the strange orbits at the edge of the solar system. It is simply the most famous one, and you owe it to your drowsy, inquiring mind to meet the alternatives, because some of them are genuinely creative and a few are delightfully weird. The first and most straightforward alternative is that there is no single massive planet at all, but rather a collective gravitational effect produced by many smaller objects. This is sometimes called the self-gravity hypothesis. The idea is that the Kuiper belt itself, or a more massive version of it that existed in the early solar system, could generate enough combined gravitational influence to sculpt the observed orbital patterns without any need for a hidden giant. If the total mass of distant icy objects is larger than current estimates suggest, their mutual gravitational interactions could, over billions of years, produce clustering effects that mimic the signature of a single large body. The appeal of this idea is its parsimony. It does not require an extraordinary undiscovered object. It just requires more of what we already know exists. The problem is that current estimates of the Kuiper belt's total mass are far too low to produce the necessary effects, and there is no strong evidence that a much more massive belt existed in the recent dynamical past. The second alternative is that the clustering was produced not by a planet or a belt but by a passing star. The Sun, like all stars, moves through the galaxy, and over its 4.5 billion year life, other stars have occasionally passed close enough to perturb the outer solar system. A sufficiently close stellar flyby could, in principle, torque the orbits of distant objects into aligned configurations. Some researchers have modelled specific flyby scenarios and found that they can produce Sedna-like orbits, though reproducing the full suite of observed features, including the clustering, the perpendicular orbits, and the detached population, with a single flyby is challenging. The stellar flyby model also has a timing problem. The effects of a flyby would gradually disperse over billions of years as the perturbed objects interact with the rest of the solar system, so the clustering we see today would need to have been produced relatively recently in cosmic terms, which limits the plausible flyby scenarios. The third alternative is more radical, and it ventures into territory that makes some astronomers visibly uncomfortable. What if the gravitational anomalies are not caused by an unseen object at all, but by a modification of gravity itself? Modified Newtonian dynamics, known as bond, is a theoretical framework originally proposed in the 1980s by physicist Mordechai Milgram to explain the rotation curves of galaxies without invoking dark matter. MOND modifies Newton's laws at very low accelerations, precisely the regime that applies to objects in the outermost solar system. A small number of researchers have suggested that MOND-like effects could produce the observed clustering without any need for Planet 9. This idea remains deeply controversial and is rejected by most mainstream planetary scientists, but it has not been conclusively ruled out, and it occasionally surfaces in the debate as a provocative footnote. Scientists still argue whether MOND is a genuine alternative to dark matter and hidden mass, or merely a mathematical curiosity that happens to fit certain observations by coincidence. The fourth alternative is perhaps the most imaginative, and it involves not a planet that formed in our solar system, but one that was captured. Rogue planets, worlds that have been ejected from their parent star systems and drift freely through interstellar space, are thought to be remarkably common in the galaxy. Some estimates suggest there may be billions of them in the Milky Way alone. It is conceivable that the Sun, at some point in its history, gravitationally captured a passing rogue planet and pulled it into a distant eccentric orbit. This captured planet could then serve the same dynamical role as a native Planet 9, shepherding the extreme trans-Neptunian objects into their observed configuration. The captured rogue scenario is not fundamentally different from the standard Planet 9 hypothesis in terms of the gravitational effects, but it offers a different origin story, one that does not require explaining how a massive planet formed or was scattered to the outer solar system from the inner regions. There is a quirky wrinkle to the rogue planet idea that deserves mention. If Planet 9 is a captured rogue, its composition could be radically different from anything else in our solar system. A planet that formed around a different star, with different chemistry and different conditions, might have an entirely alien internal structure. It could be denser or lighter than expected, with a composition that does not match any of the standard models for solar system planets. This would make it scientifically fascinating in a way that goes far beyond its gravitational influence, but it would also make it harder to predict its brightness and thermal emission, complicating the search even further. And then there is the swarm hypothesis, a cousin of the self-gravity idea but with a twist. Instead of many small objects producing a collective gravitational effect, some researchers have proposed that a dense concentration of small bodies, perhaps a remnant of a disrupted dwarf planet or a primordial cluster of material, could produce a localized gravitational perturbation that mimics the effect of a single massive planet. This idea has not gained much traction because it requires a very specific and somewhat implausible arrangement of material, but it has not been definitively ruled out either. You lie back in the dark, surrounded by competing explanations, each one plausible enough to keep alive and none quite strong enough to kill the others. The universe, it seems, is offering you a multiple-choice test with no clearly correct answer. And one of the options waiting just ahead is so strange that it deserves its own stretch of the night. You thought things were strange already, but you were not prepared for this. In 2019, physicists Jakob Schultz and James Unwin published a paper that, on first reading, sounds like something pulled from the plot of a science fiction novel that even the author was not sure they believed. Their proposal was that the gravitational effects attributed to Planet 9 might not be caused by a planet at all. They might be caused by a primordial black hole, a tiny, ancient, impossibly dense remnant of the Big Bang, roughly the mass of 5 to 10 Earths, compressed into a sphere about the size of a grapefruit. Let that settle for a moment. A grapefruit. You could hold it in your hand if your hand could survive the encounter, which it absolutely could not. An object the size of a citrus fruit with a mass of several Earths would have a surface gravity so extreme that approaching within a few meters would stretch you into a thin ribbon of atoms, a process physicists call spaghettification, which is a real term and not a joke, though it certainly sounds like one. And this thing, according to Schultz and Unwin, might be orbiting our sun right now, out in the darkness beyond Neptune, tugging on distant icy worlds with exactly the same gravitational signature as a hypothetical massive planet. Primordial black holes are a theoretical class of black hole that differs fundamentally from the stellar black holes you have probably heard about. Stellar black holes form when massive stars exhaust their nuclear fuel and collapse under their own gravity. They are typically several times the mass of the Sun and are distributed throughout galaxies wherever massive stars have lived and died. Primordial black holes, by contrast, are thought to have formed in the first fraction of a second after the Big Bang, when the universe was so hot and dense that random fluctuations in the density of matter could have caused small regions to collapse directly into black holes without ever passing through the star phase. These primordial black holes could, in theory, span an enormous range of masses, from far lighter than any asteroid to heavier than the Sun. The specific mass range relevant to the Planet 9 hypothesis, 5 to 10 Earth masses, falls in a window where primordial black holes have not been ruled out by existing observations. Now, you might reasonably ask why anyone would prefer a tiny black hole over a normal planet as an explanation. The answer is partly about solving two mysteries at once. primordial black holes in the right mass range have been proposed as a candidate for dark matter, the mysterious invisible substance that makes up about 27% of the universe's total mass energy content. If primordial black holes exist in sufficient numbers, they could account for some or all of the dark matter that astronomers have been struggling to explain for decades. Schultz and Unwin's argument was that if the dark matter problem and the Planet 9 problem could both be addressed by the same class of object, that would be an economical and elegant solution. One hypothesis, two mysteries solved. The practical difference between a planet and a primordial black hole of the same mass, from a purely gravitational standpoint, is zero. Gravity does not care about the size or composition of an object. It only cares about mass. A 5 Earth mass planet and a 5 Earth mass black hole at the same distance would produce identical gravitational effects on surrounding objects. The extreme trans-Neptunian objects would cluster in exactly the same way regardless of whether the shepherd is a cold, dark planet or a cold, dark singularity. This means that the orbital evidence cannot distinguish between the two scenarios. You need a different kind of detection entirely, and this is where the story gets even more unusual. If Planet 9 is actually a primordial black hole, it would be essentially impossible to detect through reflected sunlight or thermal emission, the methods that conventional planet searches rely on. A grapefruit-sized black hole emits no light of its own, reflects nothing, and has a Hawking radiation output so minuscule at this mass that it is utterly undetectable with current technology. You cannot photograph it. You cannot see its heat signature. The only way to find it would be to detect its gravitational effects on nearby matter or light. One proposal, put forward by Avi Loeb and others at Harvard, suggested looking for brief flares of radiation caused by the black hole consuming small objects such as comets or asteroids that wander too close. When matter falls into a black hole, it heats up enormously as it spirals inward, producing a burst of radiation that could theoretically be detected. The problem is that such encounters would be rare, brief, and unpredictable, making a systematic search extremely difficult. Scientists still argue whether the expected rate of these accretion flares would be high enough to produce a detectable signal within any reasonable survey timeframe, or whether we would be waiting centuries for a single observable event. Another detection strategy involves gravitational microlensing, an effect where the intense gravity of a compact object bends the light of a background star as the object passes in front of it. A primordial black hole at a few hundred astronomical units would, in principle, produce a microlensing signature, but the angular size of the effect would be extraordinarily tiny, and the probability of alignment with a sufficiently bright background star frustratingly small. There is a quirky philosophical dimension to the primordial black hole idea that is worth noting. If Planet 9 turns out to be a black hole, it would be the first primordial black hole ever detected, and its discovery would have implications far beyond our solar system. It would confirm a theoretical prediction that has remained unverified since the 1970s, when Stephen Hawking and others first proposed the existence of primordial black holes. It would reshape our understanding of the early universe, of dark matter, and of the formation of structure in the cosmos. A grapefruit-sized object at the edge of our solar system could rewrite the textbooks of cosmology. The odds are probably slim, but the payoff would be enormous. You stare into the void, trying to imagine something that small and that massive hiding in all that darkness, and you feel a shiver that has nothing to do with the cold. The idea that a relic of the universe's first heartbeat might be orbiting your sun is either the most wonderful or the most unsettling thing you have heard tonight. Perhaps both. You let the black hole idea settle into the back of your mind like a strange dream you're not quite ready to interpret, and you drift forward in time. Because while theorists were debating whether Planet 9 was a planet, a black hole, or a statistical illusion. Observers were quietly doing what observers do. They were finding things. And between 2018 and 2022, the trickle of new extreme trans-Neptunian object discoveries continued, each one adding a small but potentially significant data point to the puzzle. The importance of each new discovery cannot be overstated, even though individually these objects are little more than faint smudges on a detector. Remember, one of the central criticisms of the Planet 9 hypothesis was that the original clustering signal was based on a very small sample. 6 objects formed the core of Batygin and Brown's 2016 argument. 6. That is a number so small that statistical flukes become a genuine concern. Every additional extreme trans-Neptunian object that is discovered and that shows the same clustering signature strengthens the case. Every one that does not weakens it. The observers are, in a very real sense, building the jury that will eventually deliver a verdict, one faint icy world at a time. In 2018, Scott Shepard, Chad Trujillo, and David Tholen announced the discovery of 2015 TG387, a distant object they nicknamed the Goblin, because it was first spotted near Halloween. The Goblin's orbit was remarkable. Its perihelion, the closest point to the Sun in its orbit, was about 65 astronomical units, well beyond Neptune's gravitational reach, and its aphelion, the farthest point, stretched out to an estimated 2,300 astronomical units. That is a staggering distance. At aphelion, the Goblin is so far from the Sun that light takes nearly 2 weeks to make the journey. Its orbital period is roughly 40,000 years, meaning it has completed fewer than 115,000 orbits since the solar system formed. And crucially, its orbital orientation was consistent with the clustering pattern predicted by the Planet 9 hypothesis. The Goblin's orbit aligned with the other extreme trans-Neptunian objects in a way that added weight to the idea of a massive unseen shepherd. The following year brought another significant find. 2018 VG18, nicknamed Verrier by its discoverers, was detected at a distance of about 120 astronomical units from the Sun, making it the most distant solar system object observed at the time of its announcement. Verrier was so far away and so faint that determining its orbit precisely required years of follow-up observations. But its sheer distance was itself a data point, confirming that the outer solar system contains objects at extreme distances that need explaining. Shortly after Verrier came far, far out, officially designated 2018 AG37, detected at an even more extreme distance of around 132 astronomical units. The naming convention, you will notice, was becoming increasingly whimsical, which is what happens when astronomers spend too many late nights at telescopes and start amusing themselves with press releases. There is a charming tradition in planetary science of giving informal nicknames to distant objects before their official designations are assigned, and these nicknames often reveal the personality of the discoverers more than the nature of the objects themselves. Beyond individual discoveries, the period between 2018 and 2022 also saw several important statistical analyses that attempted to reassess the clustering signal with updated data. Some of these analyses supported the original Batygin and Brown result, finding that the clustering remained statistically significant even when new objects and refined bias corrections were included. Others were more cautious, suggesting that the significance had weakened somewhat as the sample grew and as more sophisticated bias models were applied. The picture was not getting clearer in the way that either side had hoped. It was getting more nuanced, which in science is often a polite way of saying more confusing. One particularly interesting development during this period was the work of several independent research groups who attempted to constrain Planet 9's orbit, using the combined gravitational effects on all known extreme trans-Neptunian objects simultaneously. Rather than simply noting that the orbits were clustered and inferring a planet, these teams tried to work backward from the observed orbits to determine the most likely mass, distance, and orbital orientation of the hypothetical planet. The results were broadly consistent with Batygin and Brown's original predictions, but with some notable refinements. The preferred mass shifted slightly downward in some analyses, from the original 5 to 10 Earth masses to perhaps 5 to 7. The predicted orbital distance also shifted in some models, pulling Planet 9 slightly closer to the Sun than originally proposed. These refinements were encouraging because they suggested that the hypothesis was converging rather than fragmenting, that different approaches and different data sets were pointing toward a similar solution rather than scattering in contradictory directions. Scientists still argue about the robustness of these statistical refinements. The fundamental problem remains that the sample of well-characterized extreme trans-Neptunian objects is still small, and each new object can shift the statistical landscape significantly. A single discovery in the wrong part of the sky, with the wrong orbital orientation, could undermine the clustering signal entirely. Conversely, a single discovery in exactly the right place could elevate the hypothesis from probable to nearly certain. The observers know this, and it adds a peculiar weight to every new data point, a sense that each faint detection carries consequences far beyond its individual significance. There is a quirky sociological observation about this phase of the Planet 9 story that is worth noting. Between 2018 and 2022, the hypothesis occupied an unusual position in the public imagination. It was too well supported to be dismissed as fringe science, but too unconfirmed to be accepted as fact. It existed in a liminal state, a scientific Schrödinger's cat, simultaneously alive and dead until someone opened the box by either finding the planet or definitively ruling it out. This ambiguity made it catnip for science journalists, who could write breathless articles every few months about new evidence supporting or challenging the hypothesis without ever having to commit to a conclusion. The public, meanwhile, seemed to have largely decided that Planet 9 probably exists, because the idea of a hidden giant world at the edge of the solar system is simply too compelling to resist, regardless of what the error bars say. You float through this accumulating evidence, each new object a tiny beacon in the dark, and you wonder whether the pattern is real or whether you are seeing constellations in randomness, the same ancient human impulse that once drew lions and hunters in the stars. The beacons are accumulating, the debate is sharpening, and somewhere in Chile, on a mountain called Cerro Pachon, a building is taking shape that might settle the argument once and for all. You've been hearing about this facility for years now, in the background hum of astronomical news, and its name has changed more than once during its long development. It was originally called the Large Synoptic Survey Telescope, then renamed the Vera C. Rubin Observatory in honor of the American astronomer who provided some of the most compelling observational evidence for dark matter by studying the rotation curves of galaxies. Vera Rubin spent much of her career being underestimated and overlooked, a woman in a field dominated by men, and naming this transformative facility after her carries a poetic justice that the astronomical community does not take lightly. It is a quirky and bittersweet detail that Rubin herself never received the Nobel Prize, despite widespread agreement that her work merited one, and she passed away in 2016 without that recognition. The observatory bearing her name may yet deliver discoveries worthy of the honor she was denied. The Vera Rubin Observatory is not just another telescope. It is, in many respects, a fundamentally different kind of astronomical instrument, one designed not to stare deeply at a single patch of sky, but to survey the entire visible sky repeatedly, systematically, and to unprecedented depth. Its primary mission is the Legacy Survey of Space and Time, a 10-year campaign that will photograph the entire southern sky every few nights using an 8.4-meter primary mirror and the largest digital camera ever constructed for astronomy, a 3.2 gigapixel monster that weighs nearly 3 tons. Each image will cover a wide field of view, and over the course of the survey, every patch of sky will be imaged hundreds of times. The resulting dataset will be staggering in scale, tens of petabytes of raw data, cataloguing billions of galaxies, millions of asteroids, and potentially a handful of extremely distant objects that have eluded every previous survey. For the Planet 9 search, the Rubin Observatory represents something close to a definitive tool. Its combination of depth, sky coverage, and repeated imaging addresses nearly every limitation that has hampered the search so far. The depth means it can detect objects far fainter than previous surveys could reach. The sky coverage means it will not be limited to the narrow strips that most targeted searches have covered. And the repeated imaging means that even very slow-moving objects, which shift only slightly from one exposure to the next, can be identified by stacking and comparing images over weeks and months. If Planet 9 is out there and falls within the predicted brightness range, the Rubin Observatory has a realistic chance of finding it within the first few years of operation. But realistic chance is not the same as certainty, and there are scenarios in which even the Rubin Observatory might miss Planet 9. If the planet is at the far end of its orbit, near aphelion, it could be fainter than the survey's detection limit. If it is located in a region of sky dense with background stars, particularly near the galactic plane, the confusion from overlapping sources could make identification extraordinarily difficult even with sophisticated software. And if the planet's orbital parameters differ significantly from current predictions, it might be in a part of the sky that the survey covers less frequently or less deeply. Scientists still argue about the probability that the Rubin Observatory will detect Planet 9 during its initial survey period, with estimates ranging from optimistic claims of near certainty to more cautious assessments that put the odds at perhaps 50 to 60%, depending on assumptions about the planet's brightness and current location. The survey is expected to begin full science operations in the near future, and the anticipation within the planetary science community is palpable. For the Planet 9 hunters specifically, the Rubin Observatory represents a kind of reckoning. If the planet exists and is anywhere close to where the models predict, this survey should find it. And if the survey completes its 10-year run without a detection, the hypothesis will face an existential crisis. It will not be definitively dead, because there will always be parameter space that any survey cannot fully cover, but the absence of a detection by the most powerful survey telescope ever built would significantly erode confidence. Some researchers have described the Rubin Observatory as the Planet 9 hypothesis's day in court, the moment when the evidence will be weighed by the most capable instrument available and a verdict delivered one way or another. There is an additional dimension to the Rubin Observatory's relevance that goes beyond Planet 9. The survey will discover thousands of new trans-Neptunian objects across a wide range of distances and orbital types. Even if Planet 9 itself is not found, this flood of new data will dramatically improve our understanding of the outer solar system's structure and dynamics. The clustering signal, or lack thereof, will be tested against a sample many times larger than what currently exists. The observational biases that the OSOS team rightly identified will be vastly reduced by the survey's uniform, well-characterized coverage. In a sense, the Rubin Observatory will not just search for Planet 9, it will rebuild the evidentiary foundation on which the entire debate rests. You picture the observatory on its mountaintop, its dome open to the Chilean sky, its enormous camera drinking in photons from the edge of the solar system. Somewhere in those photons, perhaps, is the answer. A faint dot moving imperceptibly against the background stars, cold and patient and ancient. Or perhaps there is nothing, just darkness, and the quiet hum of a universe that does not owe us the discoveries we crave. Either way, the camera will record what is there, indifferent to human hopes, and the data will speak for itself. You breathe slowly, letting the image of that mountaintop settle into your thoughts. The air up there is thin and dry and unimaginably clear. The stars do not twinkle at that altitude. They burn steady and sharp, and among them somewhere the answer is either hiding or absent. And you find that both possibilities, the finding and the not finding, carry their own strange beauty. The Rubin observatory is scanning the sky in visible light, catching photons that have bounced off distant surfaces, but there is another way to hunt for a cold, dark world at the edge of the solar system. You do not look for reflected sunlight at all, you look for heat. And this is where a very different kind of telescope enters the story, one that orbits not on a Chilean mountaintop, but in the vacuum of space, peering at the universe through infrared eyes. The James Webb Space Telescope, launched on Christmas Day 2021, is the most powerful infrared observatory ever built. Its 6.5-meter gold-plated mirror, designed to unfold like origami after launch, collects infrared radiation with a sensitivity that dwarfs anything that came before it. Webb was not designed to search for Planet 9. Its primary missions involve studying the earliest galaxies, peering into the atmospheres of exoplanets, and investigating the formation of stars and planetary systems around other suns. But its extraordinary infrared capabilities have led some researchers to wonder whether it could, as a secondary pursuit, detect the faint thermal glow of a massive world lurking at several hundred astronomical units from the Sun. The logic is straightforward. Any object with a temperature above absolute zero emits thermal radiation. The colder the object, the longer the wavelength of that radiation. Planet 9, if it exists, would have a surface temperature somewhere in the range of 30 to 50 Kelvin, which is roughly -220 to -240 degrees Celsius. At those temperatures, the peak thermal emission falls squarely in the mid-infrared range, precisely the wavelengths where Webb excels. Unlike a visible light search, which depends on sunlight reaching the planet and bouncing back, an infrared search detects the planet's own internal warmth. This is significant because the thermal emission depends on the planet's intrinsic temperature, which is determined by its mass, age, and internal heat budget, rather than its distance from the Sun. A planet that is nearly invisible in reflected light might still glow faintly but detectably in the infrared. However, the practical challenges are substantial, and they temper the optimism considerably. Webb's field of view is extremely narrow compared to a survey telescope like Rubin. It is designed for deep, targeted observations of small patches of sky, not for sweeping surveys of large areas. Using Webb to search for Planet 9 would be like trying to find a lost contact lens in a football field using a magnifying glass. You would get an extraordinarily detailed view of each tiny spot you examined, but covering the entire search area would require an impractical number of pointings and an allocation of telescope time that would make the scheduling committee weep. Webb time is among the most competitively allocated resources in all of science, with thousands of proposals submitted each year for a limited number of observing hours. Dedicating hundreds of hours to a speculative search for an object that might not exist would be a tough sell, no matter how exciting the potential payoff. That said, there are clever strategies that could make a web-based search more feasible. If the predicted search area for Planet 9 can be narrowed sufficiently by future orbital analyses or by constraints from other surveys, a targeted Webb observation of the most probable locations becomes more realistic. Some researchers have proposed using Webb not as a primary search tool, but as a follow-up instrument, confirming or ruling out candidate detections from wide-field surveys like Rubin. If the Rubin Observatory identifies a faint, slow-moving source that could be Planet 9, Webb could be pointed at that source to check for infrared emission consistent with a cold, massive planet. This two-step approach, discovery by survey and confirmation by precision, plays to the strengths of both instruments. Beyond Webb, there are other infrared strategies worth considering. The Wide Field Infrared Survey Explorer, which we mentioned earlier, already conducted an all-sky infrared survey and did not detect Planet 9. But WISE had sensitivity limits, and a planet at the faint end of predictions could have fallen below its detection threshold. Future infrared missions, including proposed successors to WISE and next-generation space telescopes currently in the planning stages, could push those sensitivity limits deeper and cover the relevant wavelength range more thoroughly. Scientists still argue about whether the WISE non-detection is a meaningful constraint on Planet 9's properties, or whether it simply confirms that the planet, if it exists, is slightly fainter or slightly farther than the most optimistic predictions. The answer depends on assumptions about the planet's albedo, its internal heat, and its atmospheric composition, none of which are known. There is a quirky detail about infrared planet hunting that deserves mention. The thermal emission of a distant planet depends not just on its temperature, but on its size and atmospheric properties. A planet with a thick hydrogen-helium atmosphere, like a mini Neptune, would have a larger effective radiating area and potentially stronger infrared emission than a bare rocky super-Earth of the same mass. This means that the detectability of Planet 9 in the infrared depends on what kind of planet it is, which is of course exactly the thing we do not know. The search strategy has to account for multiple possible compositions, each with different predicted brightness levels, which complicates things further. You imagine Webb floating in the cold at the second Lagrange point, 1.5 million kilometers from Earth, its sunshield keeping its instruments at temperatures colder than the void it is observing. Somewhere in the wavelengths it collects, there might be a whisper of warmth from a world no one has ever seen. A faint infrared murmur from the edge of the solar system, barely distinguishable from the noise, but real. Or there might be silence. The telescope listens either way, patient and precise, gathering light that left the outer darkness long before anyone thought to look for it. You pull your thoughts inward, away from the infrared glow of hypothetical worlds, and you realize that the search for Planet 9 is not just a job for professional astronomers with billion-dollar instruments. Sometimes, the most unexpected eyes are the ones that see what everyone else has missed. You have been drifting through this story surrounded by professionals, by tenured professors, and postdoctoral researchers and engineers who build instruments that cost more than small countries spend on education. But now the scene shifts, and you find yourself sitting not at a mountaintop observatory or a space telescope control room, but at a kitchen table, a laptop open, a cup of tea going cold, and a browser tab displaying a grid of blurry infrared images. Welcome to the world of citizen science, where the search for Planet 9 is not limited to people with PhDs. The most prominent citizen science project relevant to the Planet 9 hunt is Backyard Worlds. Planet 9, launched in 2017 as a collaboration between NASA, the American Museum of Natural History, Arizona State University, and the Zooniverse platform. The concept is elegantly simple. The project takes infrared images from the WISE mission and its successor, NeoWISE, and presents them to volunteers as short animations called flipbooks. Each flipbook shows the same patch of sky at different times, and volunteers are asked to look for objects that move against the background of fixed stars. A distant solar system object, whether it is a brown dwarf, a rogue planet, or the elusive Planet 9 itself, would appear as a faint dot that shifts position from frame to frame. The human eye, it turns out, is remarkably good at spotting this kind of subtle motion, sometimes better than automated algorithms that struggle with artifacts, noise, and the complex backgrounds near the galactic plane. The project attracted tens of thousands of volunteers within its first year, and their contributions have been genuinely significant. Backyard Worlds participants have identified over 2,000 brown dwarf candidates, including some of the coldest and nearest brown dwarfs ever found. Brown dwarfs are failed stars, objects too massive to be planets, but not massive enough to sustain hydrogen fusion in their cores. They glow faintly in the infrared as they slowly cool over billions of years, and they occupy a fascinating middle ground between the largest planets and the smallest stars. Finding them is scientifically valuable in its own right, and the techniques used to find them are directly applicable to the search for Planet 9. One of the most celebrated discoveries from the project came from a retired insurance investigator named Dan Caseldon, who built his own software tool to scan WISE data more efficiently and identified a record-breakingly close brown dwarf system. Caseldon had no formal astronomy training. He was simply curious, persistent, and good with code. His discovery was published in a peer-reviewed journal with his name on the author list, a testament to the genuine scientific contribution that citizen scientists can make. There is something deeply satisfying about the idea that a retired insurance investigator, sitting at home in his spare time, could contribute to our understanding of the solar neighbourhood in ways that complement the work of professional astronomers using world-class instruments. Science, at its best, is not a gated community. But has Backyard Worlds found Planet 9? No, not yet, and the reasons are instructive. Planet 9, if it exists at the predicted distance, would be at the very edge of detectability in the WISE data. It might appear in only a few frames, or it might be so faint that it falls below the noise level entirely. The citizen science approach is powerful for finding objects that are relatively bright and relatively nearby, like brown dwarfs within a few dozen light years. For something as distant and dim as Planet 9, the human eye needs help, and that help increasingly comes from machine learning algorithms trained on the same datasets that volunteers are scanning. Several research groups have developed neural networks and other machine learning tools to search archival survey data for faint-moving objects. These algorithms can process millions of images far faster than any human volunteer, and they can be tuned to detect the specific signatures expected from a distant planet, such as extremely slow motion and a particular colour profile in the infrared. The intersection of citizen science and artificial intelligence is one of the most promising frontiers in the search, with humans identifying the kinds of patterns that train better algorithms and algorithms flagging candidates for human verification. It is a feedback loop that gets smarter with each iteration. Scientists still argue about the relative effectiveness of human volunteers versus machine learning in this kind of search. Some studies have shown that experienced citizen scientists outperform algorithms in certain tasks, particularly when the data is noisy or the target signature is ambiguous. Others have found that algorithms, once properly trained, are faster and more consistent. The emerging consensus seems to be that the best approach is a hybrid, using algorithms to do the initial heavy lifting and humans to verify the most promising candidates. The Planet 9 search, if it succeeds through archival data mining, may well owe its success to this combination of silicon and human intuition. There is a quirky sociological dimension to the citizen science movement that resonates with tonight's story. Many Backyard Worlds volunteers have described their participation not in terms of scientific ambition, but in terms of wonder. They talk about the thrill of seeing real astronomical data, of knowing that their eyes might be the first human eyes to notice a particular object, of feeling connected to a cosmic enterprise that is normally the province of specialists. Some volunteers log thousands of classifications, spending hours each week scanning flipbooks with a dedication that rivals any professional researcher. Their motivation is not money or career advancement. It is curiosity The same fundamental itch that drove William Herschel to build his own telescopes, and Clyde Tombaugh to sit at a blink comparator for months on end. You picture all those kitchen tables and home offices, all those glowing screens in the dark, all those pairs of eyes scanning for a faint dot that might be the most significant undiscovered world in the solar system. The search for Planet 9 is not just a story about telescopes and equations. It is a story about the stubborn, distributed, collective curiosity of a species that refuses to accept that the map is complete. And somewhere out there on a screen you will never see, someone might be hovering their cursor over a smudge that changes everything. You blink and the smudge is gone, and you're back in the dark, drifting outward again, wondering what it would mean if that smudge turned out to be real. You pause here in the dark and let yourself imagine, really imagine, that tomorrow morning the announcement comes. Planet 9 has been found. A confirmed detection, verified by multiple telescopes, published in a major journal, trending on every social media platform before breakfast. What happens next? What would the discovery of a massive, previously unknown planet in our own solar system actually mean for science, for our understanding of where we live, and for the questions we have not yet thought to ask? The first and most immediate consequence would be a complete revision of the solar system's inventory. Since 2006, when Pluto was reclassified, the official count of planets in our solar system has stood at 8. A confirmed Planet 9 would raise that number to 9 again, though not in the way Pluto supporters might have hoped. This would not be a rehabilitation of Pluto. Planet 9, at 5 to 10 Earth masses, would emphatically satisfy the IAU's definition of a planet. It would have cleared its orbital neighbourhood through sheer gravitational dominance over the extreme trans-Neptunian objects. It would be, by any reasonable definition, a major planet, and its addition to the roster would require a rewriting of every textbook, every classroom poster, every mnemonic device that schoolchildren use to remember the planetary order. My very educated mother just served us. Nachos would need an update, and the internet would spend approximately 72 hours arguing about what word starting with N or some other letter should be appended. This is not the most scientifically important consequence, but it is almost certainly the one that would generate the most public engagement. More substantively, the discovery would transform our understanding of planetary formation and migration. One of the deepest questions surrounding Planet 9 is how it got to where it is. A planet of 5 to 10 Earth masses at several hundred astronomical units from the Sun cannot have formed in place. The protoplanetary disk of gas and dust from which the solar system formed was far too thin and sparse at those distances to build a planet of that size. The timescales for accretion at such distances would exceed the age of the solar system by orders of magnitude. So if Planet 9 exists, it must have formed much closer to the Sun and been scattered outward at some point during the solar system's early history. The most widely discussed formation scenario involves gravitational interactions with the giant planets during the solar system's turbulent youth. In the first few 100 million years after the Sun formed, the giant planets, Jupiter, Saturn, Uranus, and Neptune, are thought to have undergone a period of orbital migration, shifting their positions as they exchanged angular momentum with a massive disk of planetesimals and with each other. This period, sometimes associated with the Nice model of solar system evolution, was chaotic and violent. Planets shifted orbits, scattered smaller bodies in all directions, and may have ejected one or more siblings entirely from the solar system. The idea is that Planet 9 was originally a fifth giant planet core, formed in the region between Jupiter and Neptune, that was flung outward by a close gravitational encounter with Jupiter or Saturn. Instead of being ejected into interstellar space, it was caught in a wide elliptical orbit at the solar system's edge, where it has been quietly circling ever since. If this scenario is confirmed, It would have profound implications for our understanding of how planetary systems evolve. It would demonstrate that planet-planet scattering, a process already observed in simulations and inferred in some exoplanetary systems, played a significant role in shaping our own solar system. It would also suggest that the solar system originally formed with more giant planet cores than it currently possesses, a possibility that has been discussed theoretically but never confirmed observationally. Scientists still argue about how many giant planet embryos the early solar system contained, with estimates ranging from 4, the current number, to 6 or more. Finding Planet 9 would provide the first direct evidence that at least one additional core survived the scattering process. The discovery would also open an entirely new laboratory for planetary science. A super-Earth or mini-Neptune in our own solar system would be an object of immense scientific interest because this class of planet, while common around other stars, is entirely absent from the inner solar system. We have rocky terrestrial planets, and we have gas and ice giants, but we have nothing in between. Studying Planet 9's composition, atmosphere, and internal structure would provide ground truth data for the models we use to interpret observations of exoplanets around distant stars. It would be like finding a specimen of an animal you've only ever seen in blurry photographs taken from miles away. Suddenly you could study it up close, measure it, understand it in a way that remote observation alone never permits. There is a quirky implication of the discovery that touches on the psychology of exploration. For the past several decades, humanity has operated under the assumption that we know what is in our solar system. The major bodies have been catalogued. The planets have been visited by spacecraft. The surprises we assumed were limited to small moons and minor compositional details. Finding a massive planet that has been hiding in plain gravitational sight for billions of years would shatter that assumption with delightful violence. It would remind us that the solar system, the one place in the universe we thought we had mapped, still holds secrets on a scale we did not anticipate. And if something that large can hide that close to home, what else might be lurking in the spaces between what we think we know? You let that question hang in the dark, unanswered and glittering, because it is the kind of question that does not need a resolution to be valuable. Sometimes the wondering is the whole point, and right now, hovering at the edge of discovery and uncertainty, the wondering feels like enough. But you are a fair-minded traveller through the dark, and fairness demands that you sit with the other possibility, the one that nobody writes breathless headlines about, the one that does not trend on social media or inspire classroom posters. What if Planet 9 is never found? What if, after decades of searching, the Rubin observatory completes its 10-year survey, the infrared telescopes push to their deepest limits, the citizen scientists scan every flipbook, the machine learning algorithms chew through every archival image, and the answer is simply nothing? What if the darkness at the edge of the solar system is just darkness? This is not a comfortable thought for the researchers who have invested years of their careers in the hypothesis, but it is a thought that science requires them to take seriously. And the truth is, a null result, a definitive non-detection, would not be a failure. It would be a discovery in its own right, just not the glamorous kind. Proving that Planet 9 does not exist would teach us something important about the outer solar system, about the limits of gravitational inference, and about the subtle ways that observational bias can conjure patterns from randomness. It would be a story about the scientific method working exactly as it should, testing a hypothesis against evidence and, when the evidence does not cooperate, having the intellectual courage to let the hypothesis go. The most immediate lesson from a null result would concern the clustering signal itself. If Planet 9 does not exist, then the apparent alignment of extreme trans-Neptunian object orbits must have another explanation. The OSSOS team's argument about observational bias would be vindicated, at least in part, and the astronomical community would need to reckon seriously with how a small, biased sample can produce a statistical signal that looks compelling, but is ultimately illusory. This would have implications far beyond the Planet 9 debate. It would serve as a cautionary tale for any branch of science where conclusions are drawn from small numbers of observations with complex selection effects, which is to say, nearly every branch of observational science. A null result would also force a re-evaluation of the dynamical arguments that support the hypothesis. Remember that Planet 9 was invoked not just to explain the clustering, but also to account for the detached orbits of objects like Sedna, the population of high-inclination trans-Neptunian objects, and the obliquity of the Sun. If Planet 9 does not exist, each of these phenomena would need alternative explanations, and some of those alternatives, as we discussed earlier, are already on the table. Stellar flybys, self-gravity effects, the gravitational influence of the Sun's birth cluster, and even modified gravity have all been proposed. A world without Planet 9 would be a world where these alternative mechanisms receive much more attention and much more rigorous testing. Scientists still argue about whether the current alternative explanations are individually strong enough to account for all the observed features, or whether they require an uncomfortable degree of fine-tuning and coincidence. A null result would intensify that argument considerably. There is a philosophical dimension to the non-detection scenario that is worth contemplating in the quiet of this hour. Humans have a long and colourful history of searching for planets that turned out not to exist. The most famous example is Vulcan, a hypothetical planet that was believed to orbit closer to the Sun than Mercury. In the mid-19th century, Urbain Le Verrier, the same man who successfully predicted Neptune, noticed anomalies in Mercury's orbit that could not be explained by the gravitational influence of known planets. Following the Neptune playbook, he proposed that a small, undiscovered planet, which he called Vulcan, was responsible. The search for Vulcan consumed decades of astronomical effort. Multiple observers claimed to have seen it transiting the face of the Sun. Le Verrier himself died believing it was real, but Vulcan did not exist. The anomaly in Mercury's orbit was eventually explained not by a hidden planet, but by Einstein's general theory of relativity, which predicted a slight precession of Mercury's orbit that Newtonian gravity could not account for. The lesson of Vulcan is sobering and directly relevant to tonight's story. Sometimes the gravitational clues are real, but the explanation is not a new planet. Sometimes the explanation is something deeper and stranger, a revision of the laws themselves or a previously unrecognized dynamical effect. Now, nobody is seriously suggesting that the Planet 9 anomalies require a new theory of gravity on the scale of general relativity. But the Vulcan parallel is a reminder that the Neptune playbook does not always produce a Neptune. Sometimes it produces a beautiful, seductive dead end that, in hindsight, was pointing towards something more fundamental. And there is a quirky irony in the fact that Le Verrier, whose greatest triumph was predicting a real planet, also spent years championing an imaginary one. Genius, it seems, does not immunize you against elegant mistakes. A null result would also have practical consequences for the careers and reputations of the scientists involved. Batygin and Brown have staked significant professional capital on the Planet 9 hypothesis. They have published numerous papers, given hundreds of talks, and become the public faces of the search. If the planet is never found, their legacy in this particular endeavour would be complicated, though not diminished in the way that public perception might assume. In science, proposing a well-formulated, testable hypothesis that is ultimately falsified is not a mark of failure. It is how the process is supposed to work. The hypothesis generated a decade of productive research, inspired new surveys, motivated the discovery of dozens of previously unknown trans-Neptunian objects, and advanced our understanding of the outer solar system in ways that would not have happened without it. Even a wrong hypothesis can be enormously valuable if it asks the right questions and generates the right investigations. You sit with this possibility, the quiet, anticlimactic possibility of absence, and you find that it does not diminish the story. It changes the ending, but not the journey. And the journey, as you're discovering, is the part that matters most when you're drifting through the dark with nowhere particular to be. You drift forward now, closer to the present, to the most recent chapters of this unfolding story. Because between 2024 and 2025, the Planet 9 saga did not stand still. It evolved, sharpened, and in some ways became more interesting than ever, even as the planet itself remained stubbornly invisible. Batygin and Brown continued to refine their orbital predictions throughout this period, incorporating new data from ongoing surveys and improved dynamical models. One of the most significant updates came in the form of a revised orbital analysis that substantially narrowed the predicted search area. Their earlier work had left a wide swathe of sky where Planet 9 could plausibly be hiding, an arc spanning many tens of degrees that represented an enormous challenge for observational searches. The updated analysis, which accounted for additional extreme trans-Neptunian objects, discovered since the original 2016 paper and used more sophisticated statistical techniques to model the clustering signal, reduced the most probable region considerably. The preferred orbit shifted somewhat in its parameters, with the semi-major axis pulling inward slightly and the eccentricity adjusting to accommodate the new data. The net effect was a smaller, more defined target zone, which was good news for observers but also carried an implicit warning. A smaller predicted region means fewer places to hide. If the planet is not found in this narrowed zone, the hypothesis faces an increasingly difficult path to survival. Brown spoke publicly about these updated predictions with his characteristic blend of confidence and candour. He acknowledged that the continued non-detection was not ideal for the hypothesis, but argued that the search had still only covered a fraction of the relevant parameter space to the necessary depth. He compared the situation to searching for a set of keys in a large house. You do not conclude the keys do not exist after checking 2 rooms. You keep looking, but you also start to wonder whether they might be in the coat pocket you already checked and somehow missed. The analogy captures the peculiar frustration of the Planet 9 search, where the target could be in a region that has technically been surveyed, but at insufficient depth to guarantee detection. Meanwhile, independent research groups contributed their own analyses, and the results were a mixed bag that resisted easy summarization. A team led by researchers in Japan used data from the Subaru telescope's Hyper-Suprime Cam survey to search for faint moving objects in a portion of the predicted search area. They did not find Planet 9, but they placed new constraints on its brightness and distance in that particular region. Another group used numerical simulations to explore whether the observed clustering of extreme trans-Neptunian objects could be maintained over the age of the solar system if Planet 9 had different orbital parameters than originally proposed, finding that some configurations were dynamically stable while others were not. Each study added a brushstroke to a picture that was becoming more detailed, but not yet resolved into a clear image. One of the more intriguing developments during this period involved a reassessment of the total mass required to produce the observed gravitational effects. Some researchers proposed that a planet somewhat less massive than originally predicted, perhaps 3 to 5 Earth masses rather than 5 to 10, could still produce the clustering if its orbit had the right combination of distance and inclination. A less massive planet would be fainter and harder to detect, which would help explain the non-detection so far, but it would also produce weaker gravitational effects that might be harder to distinguish from noise and alternative explanations. Scientists still argue about whether reducing the predicted mass strengthens or weakens the overall hypothesis. On one hand, it makes the non-detection less problematic. On the other, it makes the gravitational evidence less compelling, because a lighter planet produces a weaker signal that is more easily mimicked by other effects. There was also a fascinating development on the theoretical front. Several groups published papers exploring the long-term dynamical stability of a Planet 9 orbit over the full age of the solar system. The question is not trivial. An object on a highly elongated orbit at several hundred astronomical units is subject to perturbations from the known giant planets, from passing stars, and from the tidal gravitational field of the Milky Way galaxy itself. Over 4.5 billion years, these perturbations could destabilize the orbit, causing the planet to be ejected from the solar system or to migrate into a different orbital configuration. The stability analyses generally found that a Planet 9 with the proposed parameters could survive for the required time span, but only within certain ranges of mass, distance, and inclination. Orbits outside those ranges were unstable, which further constrained the possible parameter space and, in principle, made the search more tractable. There is a quirky detail about the galactic tide that adds a layer of cosmic poetry to the story. The Milky Way's gravitational field, though inconceivably gentle at the scale of the solar system, is not zero. Over billions of years, the slow tidal pull of the galaxy can gradually torque the orbits of the most distant solar system objects, nudging them into configurations that would not arise from the Sun and planets alone. This means that the orbit of Planet 9, if it exists, has been shaped not just by its interactions with the Sun and the known planets, but by the galaxy itself. The Milky Way has had a hand, however faint, in sculpting the outermost reaches of your solar system. You're not just a citizen of the Sun's domain, you're a citizen of the galaxy, and the galaxy's gravity reaches even here, into this cold and quiet dark. You absorb these updates like someone reading the latest chapter of a serial novel that has been running for years. The plot is thickening, the search area is narrowing, the tools are improving, and the resolution, whether it comes as a triumphant detection or a quiet concession, feels closer than it has ever been. But it has not arrived yet, and in the space between anticipation and answer, there is room for one more kind of wondering, the kind that has nothing to do with data and everything to do with what it means to be a species that looks. You've been out here for a long time now, floating at the edge of the solar system, and the factual architecture of the Planet 9 story is mostly built. The evidence has been laid out, the counter-arguments considered, the telescopes described, the simulations run. But there is a layer beneath all of that, a quieter layer that has been humming since the very beginning of this journey, and it deserves a few moments of your attention before the night draws to a close. It is the question of why we care. Not why astronomers care, though their reasons are valid and well documented, but why you care, why all of us care, why the idea of a hidden planet at the edge of the solar system captivates the imagination in a way that, say, a revised estimate of the Kuiper belt's total mass simply does not. The answer, you suspect, has something to do with the deep and ancient human relationship with unseen worlds. Long before Batygin and Brown published their paper, long before Verrier predicted Neptune, long before telescopes existed at all, humans were inventing hidden planets. The Babylonians tracked the visible planets with extraordinary precision and wove them into elaborate cosmological and astrological frameworks that assumed the heavens were full of meaning waiting to be decoded. The Greeks proposed counter-Earths and invisible celestial spheres. Medieval Islamic astronomers refined Ptolemaic models with additional invisible orbs to explain the motions they observed. The impulse to populate the unseen with significance is not modern, it is primal. It is woven into the cognitive architecture of a species that evolved to detect hidden threats and hidden opportunities in a complex and dangerous environment. In more recent centuries, the tradition of hypothetical planets has produced a colourful and instructive gallery of imagined worlds. There was Vulcan, which we discussed earlier, Le Verrier's phantom planet inside Mercury's orbit. There was Phaeton, a hypothetical planet between Mars and Jupiter, whose destruction was supposed to explain the asteroid belt, an idea that was poetic but wrong since the asteroids were never a single body. There was Nemesis, a hypothetical dim companion star to the Sun proposed in the 1980s, to explain a supposed periodicity in mass extinction events on Earth. Nemesis was never found, and the periodicity it was invented to explain turned out to be statistically dubious. And then there is Nibiru, a fictional planet popularized by pseudoscientific writers who claimed it was on a collision course with Earth, a claim that has been thoroughly debunked by every reputable astronomer, but that continues to circulate in certain corners of the internet with the persistence of a particularly resilient weed. Scientists still argue about why pseudoscientific ideas about hidden planets gain such traction with the public, while genuine scientific hypotheses about the same topic struggle for attention. The answer probably involves narrative simplicity. A planet that is going to destroy the Earth is a better story, in the purely dramatic sense, than a planet that is gravitationally nudging some distant ice balls into statistically unusual orbits. But beneath the pseudoscience and the mythology, there is something genuine and beautiful about the impulse to search for hidden worlds. It reflects a refusal to accept that the map is complete, that everything worth finding has already been found. Every generation of astronomers has expanded the boundaries of the known, and every expansion has revealed that the previous boundaries were arbitrary, products of limited instruments and limited imagination rather than actual edges of reality. Herschel did not expect to find Uranus. Nobody expected the Kuiper belt to contain thousands of worlds. Nobody expected exoplanets to be so abundant and so diverse. The history of planetary science is a history of surprises, and the expectation of further surprises is not naivety. It is pattern recognition applied to the arc of discovery itself. There is a quirky philosophical puzzle embedded in the Planet 9 search that has been noted by several commentators. The hypothesis asks us to believe in something we cannot see, based on its effects on things we can barely see, using models that simplify a reality of incomprehensible complexity. In a sense, the search for Planet 9 is an exercise in faith, not religious faith, but scientific faith, the conviction that the universe is comprehensible, that effects have causes, that mathematical models can reach into the darkness and pull out truths. This faith has been vindicated so many times in the history of physics and astronomy that it would be foolish to abandon it. But it has also been betrayed often enough by Vulcan, by Nemesis, by the luminiferous ether, and a dozen other confident errors that humility remains an essential companion to conviction. You think about all the people, across all the centuries, who have looked up at the night sky and felt certain that something was hiding just beyond the edge of what they could see. The Babylonian priest on his ziggurat, the medieval monk in his scriptorium, the Victorian astronomer at her telescope, the graduate student at his laptop, the citizen scientist at her kitchen table. They are all connected by the same thread, the same itch, the same stubborn whisper that says the sky is not done telling you its secrets. And maybe that is what the Planet 9 story is really about. Not the planet itself, which may or may not exist, but the searching, the act of looking, the willingness to spend years, careers, lifetimes staring into the dark on the chance that something extraordinary is staring back. It is not rational in any narrow economic sense. Nobody is going to mine Planet 9 for resources or build a colony on its frozen surface. The search is pursued because the question exists and because humans are constitutionally incapable of leaving interesting questions unanswered. You find that comforting here in the dark. The search itself is the point. The planet is almost a bonus. You're very far from home now, farther than you have ever been, farther than any spacecraft has travelled, farther than the faintest signals of human civilization have reached. Out here, the sun is just another star, slightly brighter than the rest, but no longer dominant, no longer the blazing centre of your daily existence. It is a point of warm light in a field of cold ones, and you could almost mistake it for any other star if you did not know exactly where to look. This is where Planet 9 lives, if it lives at all, in the space between the sun's authority and the galaxy's indifference, in the margin where our solar system stops being a system and starts being just another scattering of matter in an incomprehensibly large universe. The hunt, as of tonight, is not over. That is the honest answer to the question posed at the beginning of this journey. Is the hunt for Planet 9 finally over? No, not yet. It is closer to a resolution than it has ever been, but the resolution itself remains just out of reach, like a word on the tip of your tongue or a dream you almost remember upon waking. The Rubin observatory is preparing to open its enormous eye to the southern sky. The James Webb Space Telescope continues to collect infrared photons from the deepest reaches of space. Archival data is being scoured by algorithms and human volunteers alike. The orbital predictions have been refined, the search area narrowed, the statistical arguments sharpened on both sides. The next few years will almost certainly bring a decisive answer, one way or another. Either a faint dot will move across a detector in exactly the way the models predict, and the solar system will gain a new member, or the surveys will come up empty, and the hypothesis will begin its slow, dignified retreat into the category of beautiful ideas that the universe chose not to confirm. Batygin and Brown remain cautiously optimistic, the skeptics remain cautiously skeptical, and the universe remains, as always, entirely indifferent to the preferences of the people trying to understand it. That indifference is not cruel. It is simply the nature of a cosmos that operates on principles far older and far larger than human curiosity. The laws of gravity do not care whether Planet 9 would make a good story. They simply are what they are, and the objects of the solar system move accordingly, whether or not anyone is watching. But someone is watching. Many someones, actually, on mountaintops and in control rooms and at kitchen tables, and right now, wherever you are lying in the dark with this voice in your ears. The search for Planet 9 is a collective act of attention, a slow, patient focusing of thousands of minds on a single question. And there is something noble in that. Not noble in the grand, heroic sense, but noble in the quiet, stubborn human sense of refusing to stop looking just because the answer is hard. You think back over the journey you've taken tonight. You remember Herschel stumbling onto Uranus with his homemade telescope, the musician who became an accidental planet hunter. You remember Verrier, brilliant and abrasive, predicting Neptune from a desk full of calculations and later chasing the phantom Vulcan into a dead end. You remember Clyde Tombaugh, young and patient and without a degree, blinking his way to Pluto at a comparator in Flagstaff. You remember Pluto's demotion, that little ice world stripped of its planetary title by a vote in Prague, while the public mourned as though a friend had died. You remember the clustering signal, those handful of distant icy orbits pointing in the same direction, like compass needles responding to a magnet no one can find. You remember Batygin and Brown, the theorist and the observer, the rock musician and the Pluto killer, united by a hypothesis that either represents the next great chapter in planetary discovery or the most elegant wild goose chase in modern astronomy. You remember the skeptics and their flashlight analogy, the Ossos team patiently demonstrating that what looks like a pattern might be an artifact of where you pointed your telescope. You remember the simulations, those virtual solar systems unfolding across billions of years inside humming processors, producing clustering and perpendicular orbits and solar obliquity from a single unseen cause. You remember the alternatives, the rogue planets and the modified gravity and the primordial black hole the size of a grapefruit. Each one a reminder that the universe's imagination is always wider than ours. You remember the Rubin observatory on its mountaintop and Webb at its Lagrange point, and Dan Casseldon at his kitchen table, all of them looking, all of them waiting. Scientists still argue about what the next 5 years will bring. Some predict a detection, some predict a definitive null result, some predict that the debate will continue to simmer, with new data adding complexity rather than clarity. The honest answer is that nobody knows, and the honest response to not knowing is to keep looking, which is exactly what they're doing. And now the looking is done for tonight. You have travelled far enough. The questions will still be there in the morning, patient and unanswered, and the telescopes will still be scanning, and the algorithms will still be churning, and somewhere at the edge of the solar system the darkness will continue to keep its secrets, or prepare to give them up. But that is tomorrow's business. Tonight, you rest. You feel the tension leaving your shoulders now slowly, like ice melting in sunlight that takes its time. The vastness around you, which felt overwhelming an hour ago, now feels almost protective. There is a comfort in the immensity of space if you let yourself feel it. You're very small, and the universe is very large, and there is something liberating in that disproportion. Your worries, your deadlines, your unanswered emails, they're all impossibly tiny from out here. They're subatomic, they're invisible. The only thing that matters at this distance is the slow drift of worlds and the soft pull of gravity, which asks nothing of you except that you exist and have mass, both of which you're managing effortlessly. The sun is a warm pinprick in the dark. The stars are a blanket. Your breathing is slow and even, each exhale carrying you a little further from wakefulness and a little closer to the kind of sleep that has no edges. Somewhere, perhaps, a cold planet is turning in the void, completing an orbit it began before your species existed. Or perhaps it is not there at all, and the void is simply void, and that is okay too. The mystery does not need a resolution to hold you gently. The question itself is a lullaby. Let it carry you now. Let the darkness, which is not empty but full of possibility, wrap around you like a blanket made of starlight and silence. The hunt continues, the searchers search, and you, traveller, you sleep